subtractors. Now we know that the full adder is used to perform the addition of two variables, the variable A and variable B. Along with the variable A and B, we are giving the input as a carry, that is a carry N. And by using these 3-bit inputs, the full adder is performing addition of A and B by considering the carry input, and it is generating the output as sum. Along with the output as a sum, it is a generating output as a carry. Now here the full adder is considering the input variable A 1-bit value, either 0 or either 1. Variable B as an input 1-bit value, either 1 input or either 0. Similarly, the carry is having a value either 0 or either 1. Now already we have seen the truth table of the full adder. The inputs are given as 0, 0, 0 up to the 1, 1, 1. 3 variables, so the possible 8 combinations of the inputs we have seen. From 0, 0, 0 to the 1, 1, 1, whatever the values will come, for that what the output is generating by the in the sum and in the carry out. Already we have seen and we have implemented the full adder. Now what I want to do, I want to perform the addition of the A, B and C. But instead of taking the 1-bit input, now I want to consider the input will be either 2-bit, 3-bit, 4-bit and so on. Means the variable A, suppose if I am saying that variable A, B and C are a 2-bit values, variables. So A will be 0, 0, 0, 1, 1, 0 or 1, 1. Means the variable A, instead of a 1-bit value, now I am considering the 2-bit value. So this is my A0, this is my A1. A0, A1. Now A0 and A1 is having 4 possible input combinations. Now similarly for the variable B, when I am saying that I want to consider 2-bit value for a variable B. So B can be either a 0 or either a 1. Either 0, 0 or either 1, 0 or either 1, 1. So the inputs will be B0 and B1. Now when I want to perform the addition of the variables which are 2-bit in a size, then at that time the full adder now I can use like this. Because I know that the full adder is capable to perform 1-bit addition of a 3 input variables. Now here I want to perform the addition of 2 variables and 1 carry input, and all these variables are the 2-bit in a size. So the input A and a B. Now I am giving the input A and B. The output is generating the carry. Now the input I am giving as a carry in. Out the first input is A, second input is B. The output generating is the carry. This is a carry out and the sum. Similarly, here the variable A and B are a 2-bit in a size. Means this is A0 and this is B0. Now here you can take the example A and B. Now A is a 0, 0, B may be 0, 0, 0, 1, 0, 1, 1, 0, 1, 1 and 1, 0, 1, 1, 1, 1 and so on. Means whatever the combinations of the A and B, the inputs I want to give. This is A0, this is A1, this is B0, this is B1. So I have to give the 2-bit input. But my full adder is capable to handle only 1-bit input. So I need to use the 2 full adders to perform the addition of 2-bit inputs. Now my first full adder is performing addition of A0 and B0. So the LSB of a variable A and LSB of the variable B is given as an input to the first full adder. This first full adder is performing addition of A0, B0 and the carry input C in, that is a 0th input, and it is performing the addition operation and generating a result as a sum 0 and carry out 1. Clear? Now this carry out 1 means whatever the carry input 0 is a given, this carry output is a generating as a first carry output. Now this carry output is given as an input to the second full adder. Now this is a second full adder, which is a carry input. Now the next bits of our variable A and B, that is the A1 and B1. Now I am giving as an input to the full adder 2. Now the three inputs A1, B1 and the carry in 1. Now this is the input. Now the full adder is accepting the three variables, 1 bit, 1 bit, 1 bit, and it is generating the output as a sum 1 and the carry 2. Clear? Now this is the final output, that is the carry generated and the sum generated by the full adder 2. Now this is the 2-bit full adder, how we can implement to perform the addition of the variables which are 2-bit in a size. Clear? Got it? 2-bit full adder? Yes, समझ में आ गया? Is anybody having doubt in 2-bit full adder? Whenever we want to perform the addition of the variables and the size of variables is extending than the 1 bit, then at that time we can use the full adders in parallel and we can perform the additions. So whenever we are using the adders in parallel and we are performing the simultaneous addition operation, then that type of implementation we can say that it is a parallel adder implementation. Now this is a 2-bit full adder. Now similarly, suppose if I will say that I want to perform the 4-bit addition. So I have to use 4 full adders to implement 4-bit addition. Now let's say I have a variable A and B. Now this A and variable A and B I want to use as a 4-bit values. So when the 4-bit values I want to consider for the variable A and B, so my variables will be A0, A1, A2 and A3. Similarly, my variable B will be B0, B1, B2 and B3. Now to perform addition of the variable A and B, which are 4-bit in a size, I need to use the 4 full adders. Clear? And the carry input we have to give to the first carry, second carry, third carry, fourth carry and the final carry. Now how we can implement the 4-bit parallel adder? 4-bit parallel adder to perform addition of 2 4-bit variables along with the carry input. Now for the 4-bit parallel adder, now I am going to use the 4 full adders. Now this is the first full adder. This is a second full adder, this is a third full adder and this is the fourth full adder. Full adder, full adder, full adder and the full adder. The input given is a carry input. The first carry input is given to the first full adder and the inputs given are A0 and B0. The output generating is a S0 and the carry out. That carry is given as an input to the next full adder. Because the carry is generating from LSB, we are considering into the next higher bits to consider into the addition. Again the carry generating as the output we are giving as a input to the next higher bit addition. Similarly again the carry generating as a output we are giving as an input to the next higher bits to consider into the addition. Clear? So this is the carry out, this is a carry out and final carry generating is nothing but your output, the carry generated. Clear? It may be either 0 or it may be either 1 depending on to your input values. Now the A0, B0 as a first bit input we have given to the first full adder. Now the second full adder will consider the next bit, that is a A1 and B1. And along with the carry input which is generated into the A0 and B0 addition. Now after considering A1, B1 addition along with the carry input, the output generating by the second full adder is the carry bit and the sum bit. Now this is the 0th bit of your sum. This is the first bit of your sum, and the carry generated after the second bit addition, it is given as an input to the third bit addition. Now the third full adder is considering the third bit of the inputs, that is A2, B2. It is considering the carry input and it is performing the addition. After performing addition, whatever output is generating is nothing but the S2, that is a third bit of your addition. And the carry generating is given as an input to the fourth full adder to consider into the fourth bit addition, which is nothing but your A3 and B3. After performing addition, the full adder is generating the output as a sum and the carry. Now the S3 is the MSB of your sum, S2 is a next bit and next bit. Now this is the 4-bit parallel adder. This is the block diagram. I hope all you have cleared the concept of 4-bit parallel full adder. Clear? Yes, is anybody having doubt in this? Is anybody having doubt in this?
No.
Just take down this diagram in your notebook fast. Completed? Once you will complete, tell me so we can will forward to the next point. Finished?
Yes, ma'am.
Okay. Now we'll see how to design n-bit parallel adder. Now all are familiar with how to implement the parallel full adder. Or I can say that now all of you are familiar how to design a full adder to implement as a parallel adder. Clear? Means if I will say that implement 8-bit parallel full adder. Now all of you are implement full adder, parallel adder. 8-bit parallel full adder.
Yes.
Okay.
Yes, ma'am.
Now suppose if I will say that design and implement, design the n-bit parallel adder. Now to design the n-bit parallel adder, how I can draw the block diagram of parallel adder? First full adder, second full adder, third full adder, fourth full adder up to the n. This is a n full adder. Okay. Now these full adder are accepting the inputs as let's say A0, B0, A1, B1, A2, B2 up to the AN and BN. Clear? And the carry input is also required. This is the carry in which is given as a input, carry in and the carry in. Here the carry out. And finally this is a carry out. Clear? Here C out. And the outputs generated are in the form of a sum are S0, S1, S2 up to the Sn. Okay, this is nothing but a sum and this is nothing but a carry bit. which is nothing but your final output. This is the n-bit parallel adder. Now, by considering the n-bit parallel adder, now whatever the size of a full adder will be given to you, now you can draw the block diagram of that particular parallel adder. Clear? I think all of you are clear the concept of the parallel adder. 4-bit full adder. Now we have implemented. Now suppose if I will say that implement 8-bit full adder, then at that time how many full adders you need to use for 8-bit full adder? 8 full adders you need to implement, because one full adder is capable to perform the addition of 3 inputs and size of input is 1 bit. Remember, one full adder is capable to perform addition of 1 bit value of 3 variables. So if I want to implement 4-bit full adder, I need to use 4 full adders. If I want to implement 8-bit full adder, I need to use 8 full adders. Similarly, if I want to implement 16-bit adder, then at that time I have to use 16 full adders. Clear? So that is the whole thing about the parallel adders. Is anybody having